Have you ever really thought about what it takes to make a perfect copy of something? I mean, in our digital world, it's easy, right? Just copy-paste. But in the physical world, especially in aerospace engineering, making a perfect copy is one of the most complex, high-stakes challenges you can imagine. Today, we're peeling back the layers on this hidden science of manufacturing precision.
So let's just dive right in with a question that seems pretty simple on the surface. We have all this amazing technology, 3D scanners that can capture objects down to the tiniest detail, printers that can build them back up. So why can't we just take a critical part, like a turbine blade from a jet engine, scan it, and print out an exact replacement? Seems logical, right?
Well, it turns out the answer to that question has less to do with technology and everything to do with physics, geometry, and most importantly, safety. Because getting it wrong isn't just a small mistake. It's a risk that could lead to catastrophic failure, and that's a risk that absolutely no one in aviation is willing to take. And believe me, this isn't some theoretical thought experiment. This is a real-world, billion-dollar problem that regulators and manufacturers are wrestling with every single day.
The FAA, that's the Federal Aviation Administration, even has a name for it: Unintended Dimensional Differences. Now, that sounds pretty mild, doesn't it? But it's a deceptively simple phrase for a huge problem. It means that even with the best tools, a copy can have tiny, hidden flaws that weren't in the original design. Flaws that can have absolutely disastrous consequences.
So what are these hidden traps? Why is making a copy so much harder than it seems? Let's get into the nitty-gritty.
To really get this, the FAA uses a brilliant analogy. Just think about a simple electrical plug. You could measure the thickness and length of each metal prong perfectly, down to the nanometer. But what's the most important dimension? It's not the size of the prongs themselves, it's the relationship between them, their spacing, their alignment. If you miss that hidden relationship, the plug is completely useless. That idea is the absolute core of this whole challenge.
Now, in engineering, they have a formal name for this concept. It's called a datum. You can think of a datum as the anchor point for a part. The UR here on the map of its geometry. Every single other measurement on that part is based on its relationship back to that specific datum. It is the single source of truth for the entire object.
And this is what happens when that source of truth is wrong. Look on the left, with the correct datum, everything lines up perfectly. But check out the right side. If someone reverse engineering the part chooses a different starting point for their measurements, all the little variations stack up incorrectly, and you get parts that should fit together seamlessly that now physically collide. It just won't work.
And this is where it gets really serious. This isn't just about parts not fitting. As the FAA points out, in a high-stress part like a spinning turbine blade, just a tiny bit of extra variation from a copied design can focus stress in a way the original designers never intended, and that can lead to one thing: fracture.
But wait, it gets even more complex. You see, a part's final shape isn't defined by one single perfect measurement. It's actually the result of many tiny, acceptable variations, or what engineers call tolerances. You'll have a tolerance for its position, another for the shape of its surface, and on and on. These tiny imperfections are allowed, but the key thing is, they add up.
And this is the real kicker. It's something called tolerance stack-up. How all those little individual tolerances get combined is absolutely critical. If you stack them up based on the wrong starting point, the wrong datum, you end up with very real physical differences. You can see these deviations here, making the so-called perfect copy a fundamentally different and potentially very unsafe object compared to the original.
Okay, so if copying is that fraught with peril, how do manufacturers create these incredibly precise parts in the first place? Well, that takes us into the amazing world of micron-level manufacturing. And this is not your average factory floor. We're talking about facilities that are more like scientific laboratories. You've got multi-axis machines carving out these insanely complex shapes, all happening inside rooms where the temperature, the humidity, and even the vibrations from a truck driving by outside are precisely controlled. Why? To prevent the metal from expanding or contracting even a tiny bit during manufacturing.
To put that into perspective for you, the variations they are controlling are often smaller than the width of a single human hair. Let that sink in. That is the level of obsession required to build parts that can survive the hellish environment inside a jet engine.
All right, so we've established this need for near perfection. But here's where the story takes a fascinating twist. What if the most brilliant engineering isn't actually about preventing failure, but about planning for it?
This is a total mind bender, a huge shift in thinking. The reality is, everything, no matter how perfectly it's made, will eventually wear out. The true genius of modern aerospace design is accepting that fundamental truth and then building systems that remain safe, even when they have small, predictable flaws.
And there are two main philosophies here. The old-school way was called safe life design. Basically, you use a part for a set number of flights, and then you throw it away. Period. Doesn't matter if it looks brand new. The modern and frankly much smarter approach is damage-tolerant design. This philosophy assumes tiny flaws will exist from day one, and it focuses on being able to find them and track them to make sure they never grow to a dangerous size.
Now, the only reason this is even possible is because of some incredible technology. Things like eddy current and ultrasonic scans. These are basically like giving inspectors superpowers. They let them see microscopic cracks that are totally invisible to the naked eye, long before they could ever become a threat. It's like having X-ray vision for metal.
So if that's the level of precision that commercial aviation demands, what happens when you're building something where there is absolutely, positively zero room for error? Well, for that, we have to look to the gold standard, NASA.
When you're building a spacecraft or a rover that's going to operate millions of miles from the nearest mechanic, yeah, the standards for quality and reliability go to a whole other level. Failure is just not an option.
And this level of detail goes right down to the raw material itself. For critical parts like bearings in a long-duration space mission, NASA requires steel made by a process called PSER. Just think of it as an advanced multi-stage filtering process for molten metal. Its entire purpose is to remove the tiniest impurities that could, maybe decades later, become the starting point for a stress fracture. Now that is what I call long-term thinking.
And this quote from a NASA standard just brings us perfectly full circle. Listen to this. Even NASA warns against simply copying a design, even one of their own proven designs. They call it a common mistake. So the ultimate takeaway from the agency that basically defines precision is that every new application, every new environment requires a complete rethink. You just can't copy and paste your way into space.
So from a simple electrical plug all the way to a bearing on a space probe, we are literally surrounded by this invisible world of precision engineering. It really makes you wonder, doesn't it? The next time you look at any seemingly simple object, what hidden complexities, what unseen relationships are making it all work? What other marvels of engineering are we all taking for granted every single day?